Good afternoon. Welcome to CMP201, Autoscaling, the fleet management solution for planet Earth. Are you guys having a good reInvent? Yeah? Nice. I hope you are. I certainly am. I hope you've also had an opportunity to get out beyond the conference and experience the sights and sounds of Las Vegas. So with your indulgence, I'd like to share with you a couple of my favorite and least favorite sounds. My all-time favorite sound is the sound of people making new connections at reInvent, exchanging ideas, and making the conference the exciting, creative place that it is. If you haven't taken the opportunity to meet your neighbor, I encourage you to do that after the session. They might be the most valuable resource you encounter this week. A close second, one of my favorite Vegas sounds, the sound of cards being shuffled, the dealer saying blackjack, and the click of the chips as my winnings are deposited in front of me. Doesn't happen as often as I'd like. Now, in the category of sounds I don't like, my all-time most detested sound I'm about to share with you. Awful, isn't it? That's the sound of my Amazon pager going off and alerting me to a possible issue with one of my services. And the most despicable version of this event is when it happens in the middle of the night for something that could have been prevented. And that's actually our topic for today. We're going to talk about how you can use autoscaling to avoid preventable pager alerts in the middle of the night or any time. We're going to come at it from three different angles. Firstly, we'll talk about how you can use autoscaling's fleet management capabilities to enhance the availability of your application and avoid pages. Then we'll move on and talk about how you can use autoscaling's dynamic scaling capabilities to have your application automatically change in response to changing demand. And in this case, we have a really special treat today. I have Hook Hua with me today. He's from NASA's Jet Propulsion Laboratory, and he'll share with us an extremely compelling application of autoscaling. It's used to better understand planet Earth. After that, I'll come back. We'll wrap it up with a view of the future of autoscaling, and I'll tell you how we're bringing autoscaling to ever more AWS services and how you can use it. I'd like to begin by disabusing you of three common myths. And these are things that sometimes get in the way of people even trying out autoscaling when it could be of benefit to them. First myth, my application doesn't scale up and down. I don't need autoscaling. And this actually came up in a conversation with a customer the other day. And he was telling me, look, Andre, I've got 2 instances, pretty stable demand on my application. I'm not scaling up and down. Do you have any architectural recommendations for me? And I said, well, have you considered autoscaling? And he looked at me kind of funny and said, this conversation isn't really happening for me. You're telling me autoscaling, I just told you I don't scale. I feel like you're not really listening. And I said, well, as it turns out, autoscaling has the ability to monitor your instances and automatically heal or replace unhealthy ones, even if you're not scaling up and down. So let me say it again. Even if you have no interest whatsoever in dynamically scaling, autoscaling can increase the availability of your app through its fleet management features. Myth number 2, autoscaling is hard to use. I don't know how this got out there. It's certainly the case that as you progress through your journey of autoscaling adoption, there are a couple new concepts that you'll pick up. But I'm going to show you today, you don't have to take my word for it, I'll show you in a demo that just with a couple clicks, a couple keystrokes, you can already get into the fleet management features and be improving the availability of your app. Less than a minute. Myth number 3. This is something that sometimes our more sophisticated customers encounter as they take a look at autoscaling and say, well, that sounds cool. I like the idea that you can grow and shrink the number of instances in my fleet, but I have some instances that are stateful. They're precious to me in some way. Could be a master and a master-slave type of application. Or maybe it's a game lobby that still has some players in it. Maybe even just an instance that's picked up a long-running workload. It's almost done, and I would hate for that one to be selected for arbitrary termination when autoscaling is scaling in, looking to save me money. Fair enough. It turns out autoscaling works perfectly well with stateful applications and stateful instances using a simple feature called instance protection. And I'll show you how this works in the demo. So it turns out none of these myths are true. So autoscaling broadly divides into two categories of use cases. First, fleet management and dynamic scaling. So fleet management refers to autoscaling's ability to make automatic the process of commissioning and bringing into service your instances. You can specify their properties, what type of Amazon machine image to use, for example, the relevant security groups. You can even specify customized launch flows, launch workflows. And autoscaling brings your instances into service. It even distributes them across availability zones to maximize your resilience to localized failures. So in this example here, we've got 3 instances. They're in an autoscaling group. They've been brought into service by autoscaling. They're being monitored for health. Imagine that one becomes unhealthy. Autoscaling has the ability to detect this, terminate the unhealthy instance, and replace it with brand new healthy capacity, which is created in the exact image of the other instances in my autoscaling group, placed behind the elastic load balancer. My application remained performant and available, no pagers involved. Now, dynamic scaling is a slightly more advanced use case, and this refers to autoscaling's ability to modulate your capacity in response to changing demand on the application. So in this case, we've got 2 EC2 instances. They're in our autoscaling group, and they're serving an application that happens to be CPU bound. As we play forward the example here, you can see that the CPU was at a relatively low level on average across these instances for a little while, and then it began to spike. More demand was being delivered to the load balancer. On average, my instances, which are CPU bound, increase their average CPU utilization. Autoscaling can detect this, automatically provision additional capacity, such that on average, my CPU across the fleet drops back down to the healthy level. Again, your application remained performant and available. Should utilization drop even further and my CPU go down, the additional capacity, or even some of the original capacity, could automatically be removed by autoscaling to save you money. That way you're right-sized all the time. So let's dive into fleet management a little bit more deeply here. I'd like to propose a simple test. 3 statements. If you agree with them, it's very likely that fleet management could have some benefit for you. Statement number 1. I have instances serving a business impacting application, something I care about, something that matters to me. Statement 2, if my instances become unhealthy, I would like them to automatically be replaced, please. No pagers. Statement 3, I would like my capacity to be automatically distributed across availability zones so that I'm resilient in the event of a localized failure. Stated another way, if you're only running instances that you don't care about, that are doing things that are uninteresting to you, yet you still enjoy the experience of being paged in the middle of the night to replace those instances you just told me you don't care about, and you're content to keep all your eggs in a single availability zone basket, there's probably not a ton I can do for you. I suspect that most of you agreed with at least one of these statements, so we will carry on with the presentation in the form of a demo. This is recorded because I'm chicken. So here we are in our US West 2 region. I've got 2 instances that are out there. They're just 2 instances in the wild, not in an auto-scaling group. And I went to this awesome auto-scaling presentation and realized that auto-scaling can help enhance the availability of these instances. So how do I do that? I'll go to one of them and right-click on it. If only yeah, there we are. Right-click, go to Instance Settings, and say Attach to Auto-Scaling Group. I'll give my auto-scaling group a name, and click Attach. And behind the scenes, an auto-scaling group has been created with that instance in it. So if I stopped right here, if I dropped the mic and walked off the stage, I would already have enhanced the availability of that particular instance. Auto-scaling is monitoring it for health. It would automatically be replaced without me doing anything further, without any pager alerts, just automatically. So let's go and have a look at what we've created here by following the hyperlink to the auto-scaling console. There we are. Now, a number of auto-scaling properties that we'll come back to in a second. Here is the instance that's in my auto-scaling group. Of course, you all memorize the instance ID and you recognize that it is indeed the same instance. No tricks have been played. And so if we go back to the details view, I'll show you some of the properties that we can tweak here. You have, for example, the ability to set a minimum size to your auto-scaling group. That way you're certain that automatic scaling activities never take you below a certain capacity. You can also set a maximum size. That way you have assurance that auto-scaling won't be spinning up instances and that you won't get a surprise bill at the end of the month. So in this case, I'm going to change my maximum size to 2 because my intent is to go ahead and add my second instance to the auto-scaling group. So I'll save that, go back to the instances view, and collect my second instance here. Right-click, instance settings, attach to auto-scaling group. In this case, I'm going to pick the existing auto-scaling group that I had created. Go ahead and attach that. And then back to the auto-scaling console. So here we are in the instances view. You can see the second one there. It's in the process of being attached to the auto-scaling group. While that takes place, we're going to flip over to the launch configuration area. So launch configurations are kind of the template for new instances that will be stamped out by my auto-scaling service here. So this was sucked in from the initial instance that I used to create the auto-scaling group. And it has a number of properties, for example, the security keys involved, the type of instance, the security group, and the Amazon machine image that was involved. So this all happened automatically. I didn't have to configure any of this. So the next thing that we're going to look at is this nifty feature that auto-scaling has called aggregate metrics. So this is a handy way to look at different parts of your microservices contained in auto-scaling groups and do benchmarking, profiling, even capacity planning. Because within an auto-scaling group, I can view, for example, the average CPU or different types of aggregations across network and disk I/O or memory. And so it's a handy way to see how your app reacts to changes if you're doing a deployment, for example, or just sort of if you've got usage that's steadily increasing that you may want to pay attention to. So the way that we tap into this is by going to the monitoring tab and going enable group metrics. And then I flip over to the CloudWatch console, which is of course our monitoring service where all this goodness takes place. I'm going to select EC2 metrics by auto-scaling group. Type in the name of my auto-scaling group that I created. And you can see there's a good inventory of things available to me. As I said, CPU-related metrics, memory, network, disk, all manner of things here. I'm going to select CPU utilization. And you can see at the top there, this has been running in the background for a little while here, just so we have something to look at. You can see how my CPU kind of evolved up and down throughout the day here. Not doing much with these two instances, but this is the average across the two. So it's kind of a handy view, again, for benchmarking, profiling, capacity planning, and so forth. And there's different types of aggregation. It doesn't have to be an average. It could be a min or max, even a percentile. And I can aggregate across different time periods. Okay, so let's go back to the auto-scaling console here. Now, I made a claim earlier in the presentation that auto-scaling has the ability to automatically balance your capacity across different availability zones. So I'm going to add an additional subnet or availability zone to this particular ASG configuration. Save that. and flip over to the instances view here. And let's see what we have. Okay, so this is interesting. I have 2 instances that are up and running in availability zone A. Those were the initial 2 instances that I started with. And we have a launch pending in availability zone B. This is the beginnings of autoscaling attempting to rebalance my capacity. We're going to launch an instance in availability zone B. Once that one is up and running and healthy, I'm going to terminate one of the original ones. I won't, autoscaling will. So that launch is pending, and the instance is now running, and we can see that one of my original instances is shutting down. So at the end of this process, I'm going to have 1 instance in each of the 2 availability zones. That's improved my availability posture and resilience to localized failures. Now, we talked about how autoscaling can monitor your instances and replace unhealthy ones. That's what we're going to demonstrate next. I'm going to give this instance here a label. I'm going to call it victim. And behind the scenes, you have to imagine that an impairment is about to take place that will cause this instance to become unresponsive to health checks. And what we'll see is autoscaling will detect that, terminate the instance, replace it with a healthy new one. So here we are. That instance is indeed shutting down. Eventually, it will be terminated, and we have a brand new launch pending to replace that capacity. No pagers involved. And eventually that launch will succeed, and I'll be back up to a highly available and performant state. Okay, there we go. Now, the final thing we're going to look at here is this instance protection feature that I told you about. So I made a claim at the beginning that autoscaling works perfectly well with stateful applications and stateful instances. So I'm going to go ahead and label this instance at the top here stateful, just so that we recognize it. So this instance is precious to me. When autoscaling is looking to scale in, which I'm about to cause, my desire is for any instance other than this one to be selected for termination. So how do we ensure that? Go to the autoscaling console, instances view, select that instance. It's the one in availability zone B. Instance protection, set scale in protection. And there we are. That's how I declare that this instance is a precious one. And so what I'm going to do now is change the desired size of this autoscaling group from 2 to 1, which will trigger a scale-in event. Autoscaling will be hunting for an instance to terminate, and ideally we will see that it did not terminate my stateful instance. Okay, here we are. There's an instance terminating. It is indeed not my stateful instance, not by accident. So we covered a lot of ground in that demo. We saw how autoscaling can be used with just a few clicks to start monitoring instances and replacing unhealthy ones with brand new healthy capacity. We saw how autoscaling's aggregate metrics can be used for performance monitoring, benchmarking, capacity planning, profiling, etc. We saw how autoscaling can rebalance our capacity into different availability zones, improving our resilience to localized failures. And finally, we saw how autoscaling can safely be used with stateful applications. None of this, by the way, had anything to do with dynamic scaling. This was just basic fleet management. It's an AWS best practice. Let's talk about dynamic scaling. So again, dynamic scaling is autoscaling's ability to change the size of your application, increase the number of EC2 instances, and decrease them in response to changing demand. Now, we actually have a deep dive on this whole topic tomorrow, and it's actually co-presented by Netflix, who's going to tell us about all the tips and tricks that they've picked up over their years of using autoscaling. Nevertheless, it's our intent for you to leave here today with a good understanding of how you could apply dynamic scaling to your use cases And in fact, Hook, in just a moment, will be presenting how NASA's Jet Propulsion Laboratory uses dynamic scaling to better understand planet Earth. So the simplest form of dynamic scaling is scaling on a schedule. And this takes advantage of the fact that many applications have some seasonality to their demand pattern. They're busy during the weekday, quiet at night. Or maybe quiet during the whole month and busy at the end of the month, right? Your capacity needs may change in a somewhat predictable and recurring fashion. And so you have the ability with auto-scaling to inject recurring scaling events. So we have a customer called Reckon who offers accounting software in the cloud, and they take advantage of this to scale out every weekday morning in advance of demand on their application and scale back in at night. You also have the ability to inject one-off scaling events. So if you have, for example, a marketing campaign that you know is going to drive demand to your website or to your application, or you know you're going to be featured on TechCrunch, you can inject a one-off scaling event slightly in advance of the period of high demand and then scale back in right after. So with this form of dynamic scaling, with really very little effort and industry on your part, you can effectively balance availability, performance, and cost savings. Now, the next type of dynamic scaling is something called reactive scaling, and you can use this instead of or in conjunction with scaling on a schedule. And so reactive scaling really boils down to two things. Firstly, selecting your metric. What is the load metric that indicates or that conveys the load on your application? Is it CPU bound? Is it memory bound? Something else? Select your metric, step one. The second thing is setting the target value. I would like my CPU to stay at 50%, or I would like my latency to be at 200 milliseconds. That's all you tell autoscaling, and it does the rest. Essentially scaling out and scaling in order to keep your selected target metric at the value that you've specified. It's kind of like a thermostat, turning on and off the heat and air conditioning to keep you at your desired temperature. So for those of you a little bit familiar with autoscaling, this is a new feature that considerably simplifies the dynamic scaling experience. So I'd encourage you to check it out. And again, we have the session tomorrow that goes a lot deeper. Let's look at this in the form of an example. So we have 4 instances in our autoscaling group here. They're behind an elastic load balancer, serving an application that's CPU bound. Correspondingly, I've set a scaling policy that says autoscaling, keep my CPU at 50%. Metrics are being collected and aggregated. Here we are, we have a 50% data point. Autoscaling sees this and says, 50%? That's exactly what your policy said, no action. Another 50% data point. Nothing to do here. Now imagine that demand has spiked and your CPU has gone up on average across this fleet to 65%. Autoscaling has the ability to detect this, automatically add capacity such that a new instance is provisioned, brought into service, and ultimately returns your aggregate average CPU across the fleet to 50%, which is exactly where you wanted it to be. Should demand drop, some of these instances could be taken away in order to bring your utilization back up to 50%. This is how you save money. So I'm sure it would be very interesting for you to hear me talk in the abstract about autoscaling, but I think it might be even better for us to get a little bit more concrete and hear from a customer about how they're applying autoscaling to the problem of better understanding planet Earth. Now, you've seen how easy autoscaling is to use. It's actually not rocket science. And so to prove this point, we decided to invite a co-presenter from the rocket scientist place. I think that probably worked better in my head. So NASA's Jet Propulsion Laboratory actually was one of the early adopters of AWS in the federal government space. They've been using our cloud since 2009 in order to study telemetry from some of the most advanced space robotics out there. And so it's my pleasure to introduce you to Hook Hua from NASA's Jet Propulsion Laboratory.
Yeah, thank you. I'm very excited to be here to be able to talk about some of the things that we've been doing with, not just with auto-scaling, but many of the other integrated Amazon services as well. But auto-scaling particularly has been really impactful for us in terms of how we have been able to leverage and use auto-scaling to provide that type of immediate capabilities for analysis and processing. And we'll be talking about the advanced rapid imaging and analysis, and how many of you had noticed that that kind of spells out the acronym ARIA. This is going to be the other ARIA, not to be confused with the hotel ARIA. So one of the things that, one of the major challenges that we faced over the years is that we're working with remote sensing data, and we're trying to exploit remote sensing data for doing analysis and actually looking at surface deformation type of analysis of the Earth. And typically it's been more of an artisan black art almost, as opposed to this form of automation. So we've been working a lot in terms of how we can automate a lot of these things. It's very similar to like in machine learning about doing hyperparameter optimization. It's going to be, a lot of it is going to be domain-specific knowledge. There's going to be idiosyncrasies that you have to know about in a domain. Many of the analysis that we do, it's very topography dependent. The algorithms may be different depending on where you're analyzing based on one satellite versus another satellite. And there's many different factors, but what we're trying to do is automate many of those things end to end. And we're doing actually all of this in Amazon. But these are just some of the, on the bottom, there are some of the example type of analysis results. We go through all these pipelines, but at the end, we go from raw data all the way to basically informationable products, actionable products. They may include like time series analysis of some kind of a change, some kind of a signal, or even ground deformation maps. Many of the ones that we're interested in are what's called co-seismic deformation maps, which really means they span the scope of an event, so you can actually see the impact of an event before and after an event, what actually had happened. And with ARIA, we've been actually trying to exploit a multi-sensor approach. And the one that we're really exploiting a lot on is radar sensors. And actually, to be specific, we're using synthetic aperture radar data, which is like a SAR instrument, basically. And we're doing a lot of that analysis and processing within Amazon. We use auto-scaling to kind of scale up. And the nature of remote sensing is that the data streams are not always constant. They may come in bursts, depending on what areas you're looking at. Are we looking at an earthquake? Are we responding to a hurricane? And we would monitor and process all of that continuously. But then it may spike up in activity depending on if we are responding to even a flooding event, for example. But overall, we have this end-to-end type of capability that would integrate in multiple sensors. And we want to get to that point where we're doing analysis and reaching for these type of informational, actionable products. And here's an example. This is one from last year from the Amatrice earthquake in Italy. And you can kind of see here, this is what gets processed. And when we get to the point where we have essentially what we call a data product that represents, here it is those color fringes that you see represent the surface ground deformation after the earthquake itself. So it was actually a composition of two acquisitions before and after the earthquake. So this is kind of like what we call a co-seismic interferogram. And the thing is that this is all processed using the European Space Agency's Sentinel-1A data, but it was all done in Amazon, but it was all done with auto-scaling, and it was all done automatically, meaning that there was no one that was involved in this whole end-to-end process. The system running, and this one was running in US West 2, it was fully automatic. We did not really have to do anything. And here's a more broader global representation of what we're actually doing. And a lot of these lower level type of analysis processing was actually done in Amazon. You can kind of see examples of, say, in California, you can see some of the coverage that we're doing looking at deformation near the San Andreas Fault area. There are a lot of volcanoes that we're monitoring using similar techniques. And there's actually various different, for example, the other volcano, Kilauea, and even the Agong, the recent one that exploded just a few days ago. There's also major analysis on the Rutherford ice stream down in Antarctica as well. But the point is that this is a representation of all of these different types of analysis that we're actually doing. And it needs a lot of processing power and a lot of storage. Actually, we're very I/O heavy and CPU heavy. And here is actually something that may hit home more. This is more recent. This is actually our analysis, our team's analysis from the recent Hurricane Harvey response. And what's interesting is that just to even get to this type of image, and what we're looking at is actually a flood proxy map. It's basically a map derived from the use of the Japanese Aerospace Exploration Agency's ALOS-2 data. And we were able to process this and looking at the actual amplitude signal of 2 acquisitions. And we're able to derive basically a map that kind of represents the likely areas that would have been flooded. And you can actually see major blue areas there that represents highly likelihood areas of flooding. And then more recently as well, this was actually Hurricane Maria. And then part of that effort, we were actually using ESA's Sentinel-1A and 1B satellite there. And in that little blue-orange blow-up box there is actually what's called a damage proxy map. And it kind of shows using yellow and red pixels areas that are likely to have damage. And it's actually based on the comparison of coherence signals between 2 acquisitions. And in fact, I think it was September 21st was the landfall, and we got lucky. Within hours after landfall, Sentinel-1A had flew right over that area and made some acquisitions. And the system running in Amazon with auto-scaling, it spun up overnight by itself while most of the team was sleeping, and it was able to process the data so that to the point where on the next morning, we were able to get a derived informational product sent out to FEMA, and they were able to actually integrate it in together with infrastructural maps and actually give like a density map that shows possible damage. And it was actually given to the search and rescue team, boots on the ground there. What's interesting about all of this is that to do all of this, it actually takes a team of not just geodesists and remote sensing experts and instrument experts. We have radar experts on the team as well. We also have cloud computing experts and science data systems experts. And all of this together, we are kind of integrating a large end-to-end picture of how to make this all happen inside Amazon. When you look at this, for example, this is kind of like an explanation of how we do auto-scaling. That example that we just showed was about urgent response. And this is an example of a more recent Puebla earthquake, the magnitude 7.1 earthquake. When the earthquake happened, we actually are tapped into multiple different event streams, including one from the USGS. And we're able to actually get an event information that says, for that earthquake epicenter estimate, we're actually estimating a displacement area, basically, of potential impact. And completely automatically, we look at available acquisition information from, say here, it is an example from the Sentinel-1 data instrument there. And we're actually able to see, okay, there are ascending and descending tracks. The ascending track is the green one, and the descending track is the red one. And that kind of shows us what overlapping scenes are available that overlaps with the potential area of damage. And from that, fully automatically, we do reactive auto-scaling, as Andre was talking about, where the system was able to spin up and pull down these particular scenes and then run through the production pipeline for each one of those things, and then basically stitch together these larger composites. But the thing is that it's all done fully automatically. And here's another more recent one, the Chiapa earthquake. This is, I think, a magnitude 8.1 earthquake here. And you can kind of see there on the left side, you can see those similar fringes showing the ground deformation, the aftermath of the earthquake. And also over the exact same area, we're looking at coherence change. The 2 different acquisitions, you can actually see this is a damage proxy map image of that same area, but you can kind of see lots of red regions and also some moderate yellow regions that shows likelihood of building damage probably. But this is all done automatically, and this is all done using satellite data. This is compared to, say, how things used to be in terms of they would have boots on the ground and survey the area. That may take weeks or months. This is done hours after those satellite acquisitions are made. And how we do that, we use different kinds of scaling. The first one is dynamic scaling. And in dynamic scaling, this is actually an actual plot of over time on the x-axis, and on the y-axis is the number of compute instances that we're actually using in our data analysis science data system. And you can kind of see that over the course of one day, the system's able to react dynamically by itself to go up and down as new satellite imagery is made available and as we're processing it automatically. And then there's a tail off that's scaled in right there towards the end when things are done. So, with new target tracking policies, you can actually set desired states as well, and for this type of profile to be basically fully managed by the auto scaling capabilities. And what we found over the years is that with auto scaling, it's one of the easiest ways to basically acquire something like 100,000 CPUs pretty quickly in order to do any type of bursty analysis, which a lot of is what we're doing right now with remote sensing data analysis. Here's another example from our help that we helped the NASA's Urban Carbon Observatory mission. They were doing they were calling it a level 2 full physics processing. And they asked our team to help them help to increase their production processing rate. And we were able to quickly integrate in their level 2 full physics algorithms and run this inside the Amazon cloud. And we did this with auto scaling. And this is an actual profile of us processing an entire month's worth of observations in just a few hours. And actually, that little flatlining there you see was actually the operator feeling, she set a limit. She set an auto-scaling limit to about 1,032 vCPU cores. She just felt more comfortable with that speed. And so, but that explains the flatlining. But even after a few hours of running at that rate, auto-scaling kicked in when there was nothing left to do. The system was able to dwindle down by itself. It was doing a scaling event by itself. And this bottom graph here was us kind of validating that within the Amazon ecosystem with auto-scaling going up and down, we were also tracking our overall remote sensing data throughput. And overall, Amazon was keeping up. This is actually throughput coming from S3 and other services, but that was basically our validation that as a whole, things were working pretty well. One of our other lessons learned is in the considerations for scaling and scale out. When we're scaling up, you have to be mindful of things like looking at are there any certain target tracking policies that you can actually exploit? What about the notion that when you want to scale up, let's say, 1 or 1,000 or even 5,000 instances, you won't get 5,000 instances immediately. You have to be mindful of things like batch, how auto scaling spins things up in batches, and then between each batch, there's a rest period. So understanding those little details helps us to better understand how auto scaling works. And similarly, on the scale down event, or some people call a scale in event, what we've also learned over the years is that it's highly dependent on your domain too. For us, we're very stateful oriented. Many of all of our compute instances are stateful aware. So we have to do other things like, for example, exploiting instance protection that basically says, wait a minute, we're not really quite ready to shut down yet. We need to kind of hibernate certain states before we're ready to fully shut down. And one of the other lessons that we've learned is that with auto scaling, when you combine that with something like spot instances, it is really, really powerful. You can actually save a lot of money. And as you can see there with some of the comparisons of spot as opposed to on-demand pricing, and even boiling it down to the per CPU dollar spent, it's actually very cost effective. But using that with auto scaling is, I think, where really the true power of auto scaling comes in handy. And we've seen even upwards of 90% cost savings on some instance types if you were to use the spot instance. And Andre was talking about fleet management, and this is one of our major lessons learned. With fleet management and auto scaling, you can actually end up getting more high resiliency when you're using this in the spot market. So remember in the spot market, if you get outbidded, right? Maybe not anymore with this new smooth price changes that was announced this morning, but at least in the old days, like yesterday, with spot instances, you may get terminations. And so this is a representative view of 1,000 instances. This is what 1,000 instances looks like, and split across 3 AZs. And those X's kind of represent, these random, not random, but these terminations that, you've not, that's not met your bid price, or maybe that there are instances that have been marked unhealthy. But with auto-scaling now, what we've learned is that you actually end up with a much more resilient system, because now your system as a whole, through fleet management, is able to actually ride through all of these terminations or any of these issues. It's basically fully managed for you. As a developer, you would basically have to, address your domain-specific, stateful, hibernation and saving of your state. But as a whole, your system is basically much more resilient than before. And goes back to what Andre was saying, that it monitors and heals your instances automatically at really a large scale here. This is actually a chart of what we've seen in the past, not anymore after today, but at least we hope not after today. But in the past, when we scale up, you have to factor in the market maker effect. It probably won't be as a big deal anymore, but at least in the old days, when you're using auto scaling, especially in the spot market, there are market maker effects where when people come in, other users come in and use up a lot of instances, tens of thousands of instances, for example, you can actually impact the capacity, and therefore you could see temporary spikes in the price. And this is just a plot of the cost over time, and you can see spikes. And in this example here, it actually correlates, those price spikes actually correlates with the NASA missions processing. So basically, the lesson here is that you too could be a market maker. It's not just other people. But we're hoping that with the new smooth price, spot price changes, that a lot of these issues will really be a thing of the past. But there are a lot of ways that you can mitigate that too. I think in addition to the new spot pricing increases, but exploiting like spot fleet, for example, is a great way to kind of diversify your portfolio of instances so that you become much less susceptible to these price fluctuations. This is one of our last lessons learned here, is that we've learned the hard way through scaling to thousands and thousands of nodes that you may experience something called thundering herd. And thundering herd is what happens when you have lots and lots of compute instances that are accessing, for example, an API. It actually could even be an Amazon API call. It could be an API call that says, auto scaling, I want this instance protection. But if you have 5,000 instances making that same call and they're running on the same account, you're probably going to get maybe like an API rate limit exceeded error. Because there's only so many calls that you can run at a certain time. So there are many things that you can do, one of which that we've done is jittering. We would jitter our API calls. So that basically randomizes, it smears it out over like, a 10-second time frame or a 1-minute time frame or even a 10-minute time frame, depending on your domain. And by randomizing these calls, it makes less of a load onto any type of service that you're calling. So across all these different calls, the per unit time call rate is much less. And in fact, some are even recommending using an exponential cool off of your sleep time in between some of these jittering calls. This is my last slide here. This is basically a look at what's happening with what we're working on right now. On the left there is a chart of the OCO2 project that I talked about. That was launched in 2009. And back then it was generating, I think it was about 44 gigabytes per day of derived data that had to be analyzed and processed. 6 years later, the SMAP mission was launched, and it was generating, I think it was about maybe 2 or 3 times more data than that. But exactly 6 years later, we're currently working on the NISAR mission. And there's many other missions as well, but this is a good representation that exactly 6 years apart, you can see a much larger increase of daily volume. This is reaching 100 terabytes a day of just keeping up with the data. And this is how much data that we have to use to actually analyze and process. And we're using auto-scaling as one of the key essential Amazon services to help us really support this type of data throughput rate. And I actually put in there the words keep up. And this is because this only represents the keep up rate. While this is running, we also reprocess all of the data from day one. So, and when we reprocess the data, the throughput rates could go up to 0.5 petabyte a day, for example. And so auto-scaling is one of the things that we're really, really relying on to help us, provide us with that capacity that we need to kind of keep up with these data volume requirements. With that, I'll hand it back to Andre.
Thank you. Yeah, he definitely deserves that. What a cool application of auto-scaling. And I feel really gratified, actually, that we're able to participate in this important work of better understanding our planet and providing needed information to first responders. It's a pleasure to work with NASA's Jet Propulsion Laboratory on this. Now, I promised you a glimpse into the future of auto-scaling. And that future is already here, and it has a name: application auto-scaling. So here's the idea. Thus far in the presentation, we've spoken predominantly about EC2 instances, scaling out and scaling in EC2 capacity. But I bet your application has more than EC2 instances in it. Well, why shouldn't all the elastic parts of your application also be auto-scalable? Why shouldn't they also grow and shrink in response to changing demand? Well, that's what we've already started to do. Let me tell you about a couple of ways. So an extremely common application building block beyond EC2 instances is databases at the data persistence layer. And databases are great, but they haven't traditionally been that easy to scale, let alone auto-scale. That's changed now. Amazon DynamoDB, which is a serverless NoSQL database, is now auto-scalable. Amazon Aurora, if your preference is for relational databases, is also auto-scalable. In particular, your provisioned IOPS, right, your read and write operations per second, which is the provisioned dimension for Dynamo, can now be scaled in and out in response to changing demand in each of those dimensions. And for Aurora, we can automatically scale out and scale in the number of read replicas so that irrespective of load, your customers and your applications experience consistent read performance and you save money. Beyond EC2, there are also many different types of compute that are prevalent in applications. The Elastic MapReduce service, for example, and its clusters are auto-scalable. They have been for actually about a year now. So your core and task nodes can be increased and decreased in response to changing demand. So you could set a policy, for example, to scale out in low memory conditions, and additional nodes could be added so that your tasks complete on time. The Elastic Container Service was actually the first service that we made auto-scalable after EC2. And in this case, the number of tasks in your ECS service can be increased and decreased as demand changes. And we have customers like Coursera, the educational technology company, who use this to enhance the agility with which they serve their customers' needs. Now, Hook talked a little bit also about EC2 Spot Fleet. So with Spot Fleet, using a single API call, you specify the type of instance that you're interested in and a bid price that you're willing to pay and how many instances you want, and Spot Fleet brings those into service. This is now auto-scalable as well, and you can auto-scale it based on any CloudWatch metric. So it could be your average CPU across the Spot Fleet, or it could be something like the depth of an SQS queue that you're using to buffer work for your Spot Fleet workers. So we've covered a lot of ground today. We talked about how auto-scaling's fleet management can enhance the availability of your application. We also went into dynamic scaling in some detail, and Hook told us about how this can be used to better understand our planet and provide needed information to first responders. If you'd like to learn more about the topic of dynamic scaling, I'd encourage you to check out the session tomorrow co-presented with Netflix. There's actually still plenty of room if you'd like to even reserve a spot there. And then finally, we just talked about the future of autoscaling, which is application autoscaling. So from Hook and myself, it's been a pleasure and a privilege being with you today. The way that we're going to do questions is actually outside the room because we've consumed most of our time, and we're also going to be joined by the auto-scaling team there, so we'll be equipped with a couple of people to respond to you. In closing, we'd really appreciate it if you take the time to fill out an evaluation today. Thank you very much, and questions outside starting now.